What does it mean for a wafer to be flat? At first glance, a wafer may seem like nothing more than a thin, round silicon disk. It can look almost perfectly flat to the eye. But in semiconductor manufacturing, that is not enough. When we look more closely, the surface contains height variations at very different scales. Some are measured in nanometers. Some appear across millimeters. Others affect the geometry of the entire wafer. That is why wafer flatness is not one simple idea. In this episode, we will separate the concepts that describe a wafer surface at different scales. The same wafer can produce a different answer at every scale. At the smallest scale, we examine roughness, microscopic surface texture. At a wider scale, we examine nanotopography, local waviness across a larger area. At the whole wafer scale, we examine flatness, the overall geometry of the wafer. So before asking whether a wafer is flat, we first need to ask which scale we are looking at. Think of one wafer surface viewed through 3 different windows. A microscopic window reveals fine texture. A mid-scale window reveals gentle local waves. A whole wafer window reveals global shape. The surface is the same, but the behavior we measure is not. Different observation windows reveal different surface behavior, and each needs its own way of being described. So, is a wafer really flat? The most useful answer is, it depends on the scale of observation. A wafer can look flat in everyday terms, yet show measurable differences when we inspect microscopic texture, local waviness, or whole wafer geometry. Flatness is not a single condition. It depends on how we measure. Let us begin with roughness. Roughness describes microscopic surface texture. When we magnify a wafer surface, it is not an absolutely smooth mirror. Tiny height variations remain. Roughness is the way we characterize those small, repeated variations across a very small inspection area. The important question is not simply whether height variation exists. It is how small a variation must be controlled. As semiconductor processes become more precise, even small surface changes can matter. That is why roughness is more than a visual description. It is a quality concept that reflects how precisely the wafer surface is controlled. Now move to a wider observation area. Nanotopography describes local surface waviness. It is larger in scale than roughness, yet smaller than the geometry of the entire wafer. At this scale, we look for gentle surface variations that rise and fall across a local region. A surface wave has 2 key dimensions. Wavelength tells us how far apart the variations occur. Amplitude tells us how high or low they are. Roughness and nanotopography both describe height variation, but they use different observation scales. Looking at fine texture is not the same as evaluating a broad, gentle wave. Flatness looks at the wafer as a whole. A wafer may look perfectly flat, but measurement can reveal subtle differences in overall geometry and front surface height. For example, the center and the edge may not behave in exactly the same way. Flatness is the perspective that evaluates these whole wafer differences. Flatness and thickness variation are not the same question. Thickness variation asks whether thickness is uniform. Front-side flatness asks whether the front surface geometry is flat. Because the target and the reference plane are different, these ideas should be evaluated separately rather than reduced to one number. Another source of confusion is measurement scope. Global and local use different observation units. A global result evaluates the wafer as one field. A local result evaluates a defined site. A whole wafer result and a site-specific result are not interchangeable, even when they describe the same wafer. Do not ask only for the number. Ask where it was measured. The same wafer can produce a different result when the measurement scope or the site definition changes. For that reason, a flatness value is meaningful only when we also know the observation area and its measurement conditions. Now, let us look at site flatness parameters. Start with FQA, the evaluation's starting point. Then define the site size and array. Next, choose the reference surface, back or front. Then set the reference plane used for analysis. Do not start by memorizing the metric name. Start by asking which site is being evaluated against which reference. The reference plane determines the metric name. For a back reference surface, examples include SBIR and SBID with an ideal global plane, or SF3R and SF3D with a 3-point global plane. For a front reference surface, examples include SFLR and SFLD with a least squares global plane, SFQR and SFQD with a least squares site plane, and SFSR and SFSD with a least squares subsite plane. R means range and D means deviation. The same site can produce a different metric under a different reference plane. Today, we saw that wafer flatness is more complex than it first appears. Roughness, nanotopography, and flatness describe the wafer surface at different scales. Site flatness parameters add the measurement area, reference surface, reference plane, and metric definition. The key question is not simply, is it flat? What matters is the scale, the area, and the metric used to describe the surface.